Welcome back to the next lesson on the Millar Cosmological Model, or MCM for short. Today, we're going to explore gravity, not as a mysterious force that pulls on mass, but as a memory effect written into the very fabric of space itself. In Einstein's general relativity, gravity is described as the warping of spacetime by mass and energy. That's the picture we've used for over a century, and it works really well to describe things like black holes and planetary motion. But MCM goes deeper. It proposes that this curvature is actually the surface level effect of something happening underneath, a process involving memory. In this model, all matter and energy exist within something called the memory fabric. You can picture this as a kind of cosmic blanket stretched across the universe. But this isn't just empty space, it's packed with information. This information is written by events called blips, the appearance and disappearance of quantum particles. Every time a particle vanishes, it leaves behind a little dent or memory in the fabric. Over time, these dents build up like footprints in wet sand. Regions where these blips happen more often become more compressed, like bunching up part of the blanket. This is what we call blip density. Now here's the key insight. The more blips accumulate in a region, the more tense that region becomes. The fabric gets tighter, heavier, and harder to move through. This is what we experience as gravity. Near massive objects like stars or black holes, the memory fabric is crushed together by countless arnis, those deep tension structures we talked about earlier, all clustered tightly together. It's not just mass pulling on you, it's the universe's memory getting denser and harder to stretch through. That's why time slows down near massive objects. The memory fabric has to process and hold more blip events, so it writes time more slowly. This matches real-world observations like the Hoffel-Keating experiment, which showed that clocks on airplanes tick slightly faster than clocks on the ground. It also explains why gravity feels stronger when you're near large masses, not because of invisible forces pulling you in, but because the fabric itself is more compressed and harder to move across. Now, some models suggest dark matter might be explained by strange effects in empty space. But in MCM, we keep things grounded in real physical objects, like vast regions of invisible hydrogen, or the gravitational influence of primordial black holes far beyond what we can currently observe. So, to sum up, gravity in MCM comes from regions of compressed memory, the buildup of blip events. These regions slow time and increase curvature, not just because of mass, but because the universe itself is weighed down by its own history. And while other models look to abstract fields or exotic particles, MCM points to real structures, like hydrogen scaffolding and black holes, as the drivers of cosmic structure. That's it for this session. In the next one, we'll look at how this blip density compression might help us rethink dark energy and cosmic expansion.